All right. Okay, guys, if you didn't watch that video yesterday, you're going to be a little crippled today. That was absolutely imperative that you watched it. If you didn't, you need to go back and watch it. You can try to hang on today for what we're doing, but really, have I given you all a assignment sheet?
Yeah.
I did? Okay. It's imperative that you watch it and kind of figure, because that was me kind of laying down the framework for what we're doing today. So let's take a look. What we're going to do today is now put that information together and actually start graphing these things. All right, so let me, okay, we're just going to go from this. And I am going to need, all right, so go to, I don't know, probably 137? 130, that was homework, 139. Yeah, go to 139. And I am going to now basically take what we did yesterday and show what we know today. And I'm going to have to shrink this down. Okay, so here we go. All right, so what have I given you? I've given you which function? You can't see it now because it's off the screen. So this is the f function, and I want you to sketch what the derivative of f function would look like, and to sketch what the second derivative would look like. Now, there's no exact way to know what it's going to look like. I mean, there is if you got a calculator and you really had precision, all right? But we can get pretty close. All right, we might not know exactly how high it goes because I actually don't know the actual equation that created this, but we can get pretty close based on the connections that we know through this chart that I'm begging you to have memorized and burned into your brain, which is what? When f increases, the first derivative is greater than 0. And when f decreases, the first derivative is less than 0. And if I take the derivative of both sides, when the first derivative increases, the second derivative is positive. And when the first derivative decreases, the second derivative is negative. And when the second derivative is positive, what does that tell you about the function? Concave up. And when the second derivative is negative, what does it tell you about the function? Now, hopefully you can get to where you can actually crank this sucker out. I will say, please don't do this wrongly, though. If you get your test and you sketch this out wrongly on your test, oh my gosh, you are going to get just destroyed. Because you're going to literally be taking this false information and bludgeoning your test with it. So make sure it's right. Okay? I've seen that before, and I'm like, I almost want to weep for them. They're like, oh no. Because everything, they continue to look at this bad precedent. All right? So what do I know about the function here? I know a couple of things. Like, what do I know, say, about from here to there at the top? The function is increasing. So to right up to there, right, I'm going to draw a little dotted line. The function is increasing. Well, what do I know about when the function increases? The derivative is positive. Now, what is the derivative? If this is the derivative function, what does positive mean? Above the x-axis. So I'm going to draw this line right here. And I'm going to go, oh, so for the derivative function, I know it's positive. So the derivative is positive here. That's good to know. That means it's going to be somewhere up in this section right here, right? Now, what do I know at the very top? The top is a relative max, right? So if that's a relative max up there, what do I know about relative maxes from the first derivative test? The derivative is 0 or DNE. It's 0 in here, right? So the derivative is 0. I know that. But I also know that the derivative on a relative max, the derivative goes from, it's increasing, so positive to negative. So that means this derivative curve has to go from the positive side to the negative side right here. Which makes sense, because I know the derivative is positive up here, and I know it's negative right there. So one thing I like to do right off the bat is look at where all these slopes are 0, all these derivatives are 0. Take all these places, there's one up here too, but I don't have any place to write, and go ahead and just mark them as intercepts. And Now make these lines as vertical as it possibly can. And if there's a max there, right, you know that it was because F increased, and then F what? F decreased all the way through here. So if F is decreasing, what do you know? The derivative is negative. So this is going to be negative all down and through this whole region, isn't it? And then once it hits 0 again, then what do you have? F increasing, F increasing. So it's going to be positive through this region, right? And then right here, you got F decreasing. You're going to wonder why in a second why I'm doing that, but I'm writing it twice for a reason. So decreasing means it's negative down through here. And then finally, F increasing the rest of the way, which means it's positive up here. Now from that alone, look at it. You can kind of see it, right? But let's be even better. What else do we know? This is me taking what I know about F. F increasing. But what else do I know about F looking at this thing? Concavity. And concavity also points to the first derivative, just like increasing, decreasing points to the first derivative. So I can get more information out of this first derivative function, can I? So, what do we know about concave up? Now, where is this graph concave up? Looks like from right here, this is all concave up to right, maybe there, right? So maybe from right there to right, here, I'll make it. You kind of follow me? Maybe from there to there, it looks concave up? So if the function's concave up there, so this whole section, the function's concave up, what does that mean about the first derivative? It's increasing. So I'm going to take these 2 points, and I'm going to bring them down, and that means the function is increasing there. Huh. So that means increasing means this thing all the way through there is going to be going that way, right? Now, what about this concave up? From there all the way forever, what does that mean? Well, same thing. From somewhere in here to forever, it's increasing. Now, you might have looked at that and said, well, I already knew that, right? Because I was going negative to positive there. And that makes sense here. I'm going negative to positive there. Of course, it's going to be increasing there and increasing over there. And also, what do you see? On the concave down, what would that mean about the first derivative? So on these other ones, it's decreasing. But you might look at that and go, duh, I already knew that, right? Because you can see the plus minus stuff. Now, what do you know about inflection points? There's one there, and one there. It's where the second derivative is 0. And if the second derivative was 0 there, what do you think that meant about the first derivative? There's a relative max or min on the first derivative function. Does that make sense, what I'm saying? Yes. Now, it might be a layout, possible, but let's take a look. Right here, if it's an inflection point, actually, not going to be a layout on that, but on this right here, also I want to show you something. What's happening to the slopes? The slopes are 0 here, the slopes are 0 there, right? What happens as the slopes, as you start heading this way? They start getting more and more negative, don't they? So they're decreasing in value. And then what happens to slopes from here? Then they get closer back to 0, so they increase. So the slopes decreased, increased. This is the slope curve. So what's the slope curve going to do here? Decrease, then increase. There's your relative min on the derivative curve. Right here, what happened to these slopes that my hand is on right now? They're really big, right? Maybe a slope of 7 or 8, slope of 5 or 4, slope of 2 or 3 or 1, and then the 0. So these did what? The slopes decreased, didn't they? Well, if the slopes are decreasing, then shouldn't the slope function be decreasing on that interval? You kind of see how this all comes together? Yeah. Now, it's really easier to kind of memorize patterns like, hey, relative maxes on F become zeros on F prime. Inflection points on F become relative max and mins here. So once you get that down, you can go, oh, well, now that I have my zeros on F prime, my zeros on the derivative, I could mark relative maxes and mins on f prime, and then I can just come in here and kind of connect the dots. And I can make short work of this. Are you seeing this? But I'm going to want to see on your test, did you line these things up? You see me lining up inflection points become maxes and mins, right? Relative maxes and mins on f prime, and relative maxes and mins on the function becomes zeros, unless they're undefined. We can get more tricky than this. There's no cusps on this thing. There's no corners. That would look a lot different over here. And look, I just drew a pretty decent little curve. And by the way, if I were to ask you about this polynomial, wouldn't you look at this and go, there's 1, 2, 3, 4 because of the bounce, 5. Wouldn't you say that this is a y equals some positive number x to the 5th curve? What happens when you take a derivative of that? So you get an x to the 4th curve, 1, 2, 3, 4. So it still kind of makes sense, although I don't know exactly how low or high these go, and neither do you. I don't know exactly how quickly this thing goes up, neither do you. But what you do know, you should be able to mark these, and you should be able to mark those from this information.
Do the second derivative really have 3?
Do what?
The second derivative really have 3?
3 zeros?
Yeah.
Yes. And now, to go to the second derivative, you're literally doing the same thing, but now you're pretending this is your original function. But, just to point out that we know more, because we also have this, there is a link between the function and the second derivative, isn't it? But there's plenty of links between the derivative and the second derivative also. So I can use now information from the first derivative to help me with the second derivative, and I can use information from the original function. So let's check it out. What's the first thing I know? And I'll show you both ways. What does this right here represent that I'm pointing to? This is the slope of the what? Of the f prime curve. What's the slope of the slope curve? That's the second derivative, right? The slope of the slope curve, and it clearly is 0 there. So if the second derivative is 0 there, that becomes a what? Yeah, it would be a possible inflection point, and you already know it's an inflection point because you saw it change concavity up here, right? But you definitely know it's a 0 there because this is the second derivative curve. Now you could have also looked up here and went, wait a minute, I know that's an inflection point. So if it's an inflection point because it changed concavity there, that would mean that the second derivative is either 0 or dne. The only way to be dne is in Akram asked about that this morning. It'd be dne if it went vertical, right? Which is not going to happen on a polynomial. It might happen on some weird powered function. I could totally draw it in there to do that. And in that case, you wouldn't have a 0 here. It'd be dne, so it'd probably look like a vertical asymptote. But you'd have other information that would help you on that. We'll get to those. We'll graph some of those. So I'm going to go ahead and mark these. There's an inflection point that was also on f, that was also a relative max on f prime. I can go ahead and bring that down. That's totally a 0. There's an inflection point on f, which is a relative min on f prime, which is a 0 there. Right? And if you look at this, what do you know about the first derivative? When the first derivative is increasing or decreasing, what happens on the second derivative? The second derivative would either be positive or negative. So let's start with this. What's happening on the first derivative right here? It's decreasing. So the first derivative decreases. That means that the second derivative would be negative. So here's my second derivative. It must be coming up from down here because it has all negative values there. Now, once you hit that, now what is the first derivative doing? Increasing. And if the first derivative increases, what must happen? Second derivative must be positive. So on this whole interval, I got to be positive. But I also got to go through those zeros, don't I? So kind of makes sense that it would go up and down, but I'll make more sense of that in a second. Right here, first derivative decreases, second derivative negative, but it goes from 0 to negative to 0, right? And then here, first derivative increases, second derivative positive. And doesn't it make sense when I take a derivative of an x to the 4th curve that I get an x cubed curve?
Would the critical numbers become the relative maxes and mins?
Okay. Yes. No, you're talking about our critical numbers on what?
On the, or no, where, f prime equals 0.
So right here, that right there became a 0 right here, and this 0 right here becomes a what?
Relative maximum.
No, that's a,
Or is that just a coincidence?
It's just a coincidence.
yeah.
The zero is not the exact inflection.
Now, how about this? What's happening to the slope? Right here, the slope of this is something, and it's going bigger. The whole thing is slopes are getting bigger all the way through here. Does that make sense? Slopes are really negative, but they're slowly approaching 0, right? And they slowly approach 0 until they hit that. I'm sorry, they slowly get bigger, all the way through 0, even more positive, right? So right there, the slope of the slope curve is doing what? Increasing. It's getting bigger. So that would mean the second derivative is getting bigger. So right here, is the second derivative getting bigger? Actually, maybe it does. Hold on. So all the way through to there, is the second derivative getting bigger?
Yeah.
Yeah, it's getting bigger. Now what happens from right here? Say it was positive 1. It's going to 0, and then what? Into the negatives. Couldn't you say from here to here, the slopes of the slope curve were getting smaller? So the slope of the slope curve means the second derivative. Second derivative is getting smaller in value, right? What happens from here on?
Begins to increase.
It starts to increase and get bigger. Not it, but the slope of the slope curve, which is the second derivative, increased. So the second derivative values increased. Right? Now look back up here. What did inflection points on F become on this?
On F prime or F?
What did What did inflection points on F become on F prime? Relative maxes and mins. Well, wouldn't it make sense that inflection points on F prime would also do the same? So inflection points on F prime also end up becoming relative maxes and relative mins. So that was true, actually. But I don't memorize any of this junk. I don't. Some of it I do, because I've done it so much, but a lot of the real tough questions that people ask me, I'm like, well, let's take a look. To me, it's not worth memorizing. Maybe it is.
It makes more sense, like, looking at it like that than just memorizing.
I agree. And the great thing is you know how memorizing works. You might be good for the test, and then in a month I come back to this and you're like, oh crap. But if you know this, you can navigate your way through these. Your thing is, can you navigate quickly enough to finish your test? So you do have to know it pretty well. You can't completely wing it. But you're going to practice some of these. Somebody.
Is the first part concave up or concave down onto the F whole prime?
This arrow here would be concave down.
Okay.
But we don't have anything where the second derivative is concave down. The only thing we know about is if the original function's concave down. For the second derivative to concave down, I'd have to have information about the third and the fourth derivative. We won't even get there. We don't do that. I don't even know what that means. Like, for instance, you take a derivative of position, you get velocity. You take a derivative of velocity, you get acceleration. Take a derivative of acceleration. Heck, ask your physics teacher. I don't know.
Mr. Hill tells us it's jerk, snap, crackle, pop. Are the next
So
derivatives.
it's jerk.
Yeah, the jerk is 3, snap is 4, crackle is 5.
Oh, there is actually a crackle. He's not making
There's
stuff up.
no, there's
Yeah,
crackle, then it's pop, then it's lock and drop.
That sounds like some
Totally
physics
original.
teachers, embracing some foreign objects and then getting together and having a good time naming stuff.
Apparently, like, the only time they ever used it was with, like, the Hubble telescope.
Huh. Yeah, I don't know much about that.
There's there are also integrals.
But everything he does right, it's because of Mr. Homer's. I had him a couple of years when he was here. Pretty good guy. We'll leave that there. All right, now, here's what gets a little trickier. Most people have a pretty, I'm not gonna say easy time, but they do all right moving from here, and I call it moving down. Moving it, like you're basically taking the derivative of the function, okay? Now, what if I give you this? So I give you f prime, and I ask you to find the original function. Now this is where it starts getting trickier, because you're going backwards. So but I have lots of information about f prime, right? Like if I know that f prime is this, or this, or this, or this, I can link it to what? F's behavior. So literally, that's what I'm going to do. What do I know about f prime from here to here? F prime is increasing. So if f prime increases up to here, what do I know? F prime increases. What do I know about the function? All right, so I come up here and I go, all right, this thing's concave up right here. I'm just going to put that up there for now. I'm going to bring all my information up and then sketch it. So every place it's increasing, okay, here's another place it's increasing from there to there, concave up. It's increasing from there on, concave up, and then it's decreasing everywhere else, right? Oh, yeah, decreasing everywhere else, so that must be concave down. So there's my first bit of information I have. Feeling good already? Now right now you can look at it and go, look, increasing, decreasing, increasing, decreasing, increasing. I probably got a lot of inflection points there because there's no place where stuff's undefined. So lots of inflection points, but let's talk about something else. What else do I know about the first derivative? Isn't the first derivative, like right here, have negative values? Okay, so what does that mean when the first derivative has negative values? When the first derivative is negative, the function, so it decreases on that part, right? Now from here to here, the first derivative has positive values. So what does that mean? The function increases through there. Now it's 0 there, right? And 0 here. So I'm going to mark a 0, it's flat right there. The first derivative is 0 there, so it's flat right there. All right, what about here? It's all positive again, so I'm going to bring that up. And that's more increasing on the function. But again, 0 here on that almost to the second to the last intercept. So I'm going to put a little flat spot up there. That makes sense? Because if the slope is 0, then the slope would have to be flat on the original function. If the value of f prime is 0, then the slope would be 0 up here. And then right here, it's all negative, so it's going to decrease till you hit that. And then again, it's 0. And then the slope is, the derivative is positive here, so the slopes are positive up here, that be increasing. Now here's something you don't know. A lot of times in physics, you guys have gotten to this. We have a new physics teacher, he might do different things in different orders. And I'm grateful for that, because I like to change from what I'm seeing. However, when you take a derivative of something, check it out. Like if I took a derivative, say I had this function. I take a derivative and what disappears? The constant. It goes to 0, right? Now, would it still have been 0 if that was a 2 or a 12 or a 20 or a 200? Okay, well when you integrate something, when I integrate something, what happens is I go back to the original function. Problem is, I don't know whether it's 2 or 12 or 20 or 200. So I get this constant. Now, when you do a derivative, an integral from a certain x value to a certain x value, then those c values get canceled and you get an exact amount. But when I don't know, and I'm doing a general derivative, not a specific derivative from an a to a b or a certain x to an x, I get this c. What do you think c does to my graph?
It makes it larger.
It makes it go up or down. Like think about it, when x is 0, y is c. It's kind of like the y-intercept. Well, if the function has the same general look, this parabola has the same general look, right? The c value is just moving it up and down. I don't know how high or low it goes then. So when it comes to sketching it, what does not matter at all? The high or low. You could start this thing down here. You could start this thing up here. This x-axis means nothing to you. It does not matter. I will not even be looking at that x-axis when you sketch this. Are you with me on that? So know that when you sketch these and you're looking at your key, you're like, Ugh, I got different x-intercepts. Who cares? You have no idea how to know that. And when it comes to how do you sketch it, when I look at this, what does it look like the graph's doing? Down, up, up, down, up. I got 3 ups and 2 downs. So I'm going up more than I'm going down. Maybe start a little lower. Give yourself room to do those ups. Y'all with me? So I'm going to start lower here. Now, just check it out. Right here. What does this graph tell me to do now? It tells me to decrease the F while being concave up. And to be flat right here, because I brought all the information up. So I'm going to start down here. Decrease the graph while concave up. And be flat right there. Now, from this to this dotted line, what does it tell me to do? Increase the F while being still concave up, right? But what happens between these two? Concavity changed. Inflection point. Change concavity, inflection point. So I'm going to still increase a concave up. Inflection point. What happens next? More increase, but concave down. Another inflection point, and that inflection point might be below the x-axis, above, who cares? That part does not matter. But then again, look, I know it's 0 there. I mean, I know the slope, the derivative is 0, well then the slope has to be 0. All right, so it's got to be flat there. But then what happens? More increasing, more concave, or now go concave up. All right, another inflection point. Next, more increasing, but this time concave down, but flat at the top. And then more decreasing, more concave down, inflection point, more decreasing, but this time concave up, flat, more increasing, but more concave up. And the x-axis means nothing here. So your graph might have more of a tilt or whatever, but when I look at your graph, I should see relative maxes. I mean, mins there, inflection point, layout, inflection point, relative max, inflection point, relative min. I should see those because that's what this little sketch does. This little up and downs and the concave ups and stuff helps me with. Yes?
Well, is it not an inflection point? Like, can I point?
Sure.
Because like here?
Yeah. There's an inflection point on this,
Yeah, that's what I meant. Like,
but not an inflection point on that.
wait, so I'm confused. So like you know the brown marks? Those are inflection points, right? Like on the
These are,
like
no.
the brown lines. Like
That is a relative min on f. This is the f function. So that is a relative min on f, which becomes a 0 here. This is an inflection point on f, which becomes a relative max, relative max, relative min, right? Because inflection points on f become relative maxes and mins on f prime. But going the other way isn't the same truth, right?
Does a 0 on F just like become nothing?
A 0 on f, yeah, I got nothing about that.
Yeah, it just like doesn't.
Yeah. Go with me on this? And again, that's as hard as it's going to be. And you really lose information going, if this had been f double prime, and I said sketch f prime, you lose a little bit because you kind of lose the c value. Well, if I have to go up another level, you lose even more. So much of the integrity disappears when you do that. Most of the time, and you saw it actually on your test, when I gave you the 9 weeks test, the other ones I omitted, that's all over the AP test. And some of you got it right, which is amazing, because we barely talked about it, but you really thought through it. Some of you got some of them right. And it's pretty tough to get them right because there's so many different, you couldn't just guess.
Are we gonna get this back?
No, but if you want to look at it, just come for after school. That's for me. I like to assess where you are, but it's not an assessment I use. I don't have the time to talk about it, honestly. But I will before after school if you want to see it. Have y'all seen this? When's the bell ringing here? 3 minutes. So real quickly, if I can try to get this done, this is f prime. What would I know about f double prime? F prime, I know that I always go to maxes and mins first. So these would be what? That would be where the derivative of the f prime is 0. That means f double prime is 0. F double prime is 0. Well, if that's the case, bring those down. I'm just bringing those down really quickly, right? And then what do inflection points on a function become on the next one down? Relative maxes and mins. So I know that's either relative max or relative min. But even more, I know it crosses here. If f, this is f prime right here. This is f. If f prime increases, what's the second derivative do? Positive. So I know from on this whole section where f prime is increasing, f double prime is positive. On this section where f prime is decreasing, f double prime is negative. So I could really just come in here and sketch this graph right now based on that alone. But it's nice to know, oh wait, inflection points become what? No, the inflection points here become the relative maxes and the relative mins. So you could come in even after the fact and go, oh yeah, make sure you have those in there. Sketching the derivative.
How do we know that like the ends are concave up, or do we just like sketch them?
I didn't even make any, I don't know anything about this concavity
Yeah, so it just.
because I don't do concavity on the second derivative. There's nothing about concavity.
Yeah, so it just isn't.
It just kind of happened. I mean, there is a relationship there, but we don't need it to get a decent sketch, do we? So I didn't even talk about the concavity here, but I did notice about these second derivatives being 0, meant they were zeros there. Y'all seen this? Hey, these can get much trickier. So see what you can do on this homework. You do not want to take, I'm giving these homeworks to see what you can do, and then hopefully you'll ask or send me questions and get better on these. All right. Y'all have a great weekend.